Hello, everyone, and welcome to my notes on Chapter 8. This is part 2 of the notes, and today we're going to be looking at momentum and kinetic energy in collisions. I refer you to page 11 in your note packet. So hopefully, after taking this lesson, you'll have a better sense of how billiard balls behave, for instance, if we are doing a break shot or something like that. As my uncle said when I first started learning physics, physics is all about the collisions. All right, so let's talk a bit about momentum and kinetic energy in collisions and the two types of collisions, or the two broad categories of collisions that you can have. In a closed and isolated system, that is, if there are no external forces acting on your particles as they collide, if you have two colliding bodies and the total kinetic energy is unchanged by the collision, then we say the kinetic energy of the system is conserved, and this is what we call an elastic collision. So again, this is only applicable if there are no external forces that are acting during the collision. And what that means is that the kinetic energy of your two objects before the collision, so this guy is coming to my left hand is coming to the right, and it goes like that. The kinetic energy before the collision is the same as it is after the collision. Now, it's very important to note that the kinetic energy of each individual object is not going to be the same, or is not necessarily going to be the same as it was before the collision, only that the total kinetic energy is the same. So again, if we have a stationary object here and an object that's coming in to collide with it, this object is going to start moving. My right hand is going to start moving, which means that it's going to gain more velocity than when it started, which is where it started stationary. And then this object, which is moving very quickly, is going to slow down. But the kinetic energy of both of these together, so if I add the kinetic energy in this fist and the kinetic energy in this fist, it's going to be the same before and after the collision. And that is the definition of an elastic collision. Or another example, which is given by these notes, is if you have two gliders, so you have a frictionless surface, and if you put a spring in between them, there's going to be a collision. The kinetic energy is stored as potential energy in the spring. The spring springs back, and both of these sliders go back outwards with the same total kinetic energy as before the collision. Again, this does not necessarily mean that they're going to have the same velocities, either the same velocities as each other or the same velocities they had before the collision. Again, it depends on what the relative masses are of A and B, but the total kinetic energy in the system is conserved. Another way of thinking about this, or get another example of an elastic collision, is if you have a super ball. So one of those really, really bouncy ones that you drop from some height, and you'll notice that the ball rebounds off of the floor and comes roughly to the same height as to when you dropped it. And that's an example of something that's close to an elastic collision. It's not a perfectly elastic collision, but it's another example. If it were to attain exactly the same height, then it would be a perfectly elastic collision. If, however, you are losing some of that kinetic energy to some other form of energy, such as thermal energy or energy of sound, or deformation of your individual particles, then the kinetic energy of the system is not conserved. And that is what we refer to as an inelastic collision. So if I throw something against a wall and it just barely springs off of it, it comes into the wall with a tremendous thwack, and it just kind of falls, limply to the floor. That's an example of an inelastic collision. Also, if I had, say, again, a ball of Play-Doh, and I threw it against the wall, or say silly putty, and I threw it against the wall, what you would find is that the shape of the ball would not be the same as when you threw it against the wall initially. So there would be some plastic deformation which would take place, and that's another place where the energy goes. Remember that the total amount of energy in the universe is going to be the same before and after the collision. So it's not like energy is suddenly disappearing down some rabbit hole. It's just being transformed into a form that is not kinetic energy. So again, that's heat energy, that's sound energy, that can be deformation, those sorts of things. So in an inelastic collision, some energy is lost to the outside world, to the outside universe from the system that you're analyzing. If the inelastic collision causes two bodies to stick together, then the greatest loss of kinetic energy occurs, and this is what is known as a perfectly inelastic, or completely inelastic, or totally inelastic collision. So an example of this would be if I were to throw two balls of Play-Doh together and they were to stick, and then they were to continue onwards as one object, that's a perfectly inelastic collision. Or again, if you had something that was very gooey and you threw, gooey things together and they were able to continue onwards as one mass, that would be a perfectly inelastic collision. In our glider example, rather than having this spring between A and B, let's say that we put in some Velcro, registered trademark, and these two sliders were to stick together and continue onwards behaving as one mass. That's an example of a perfectly inelastic collision. In an inelastic collision, so when you're looking at types of collisions, you say an inelastic collision is one where the total kinetic energy after the collision is less than before the collision. And if the bodies stick together, that is a perfectly inelastic collision. However, in any collision in which external forces can be neglected, the system is what we call a closed system, and linear momentum is conserved. Even in an inelastic collision, momentum is conserved. That's very important to note and remember, and also remember that momentum is not energy. Momentum is a different quantity and it's a different idea than energy. So remember, even in a perfectly inelastic collision, assuming that there are no outside forces pushing on this, linear momentum will be conserved. We'll see what that means in just a moment. In elastic collisions only, total kinetic energy is conserved. So if you have a loss of kinetic energy, that's an inelastic collision. If you have a retention or a conservation of kinetic energy, that's an elastic collision. But in both cases, in both kinds of collisions, the linear momentum is going to be conserved. So I know I'm beating that to death, but remember, momentum is not energy, and momentum is conserved in all collisions unless there is some external force. All right, so let's take a look at an inelastic collision where only conservation of linear momentum applies. What does that mean? Well, it means that the momentum of the system initially is going to be the same as the momentum of the system finally. All right, so the m1 times v1i plus m2 times v2i is going to equal m1 vfi plus m2 vf2. Sorry, I've kind of changed my subscripts around here, but you get the idea that the momentum of mass 1 and the momentum of mass 2 is going to be, let me try that again. The sum total of the momentum of the first object and the second object is going to equal the sum total of the momentum of the first object and the second object in both the before and after cases. So the initial amount of momentum is equal to the final amount of momentum, and this is summed across all of the objects that we are analyzing. It's very important to note that the momentum of individual objects may change, but the sum total of the momentum between the two objects is not going to change. All right? So let's take a look at a sample problem. We have this toy delivery truck with a mass of 20 grams, and it's traveling along a level tabletop at 0.5 meters per second. In the opposite direction is a pickup truck with a mass of 5 grams, and it's going in the opposite direction at 0.75 meters per second. After the collision, the toy delivery truck continues in its original direction at 10 meters per second. So there are a couple of important things to note here. Because this is occurring along a level surface or along a level tabletop, there is not going to be any external force or any external net force from gravity, for instance. We're meaning that this is a closed system. And yes, there might be friction, but let's neglect friction, at least for the purposes of this problem. All right, so we know that. We also know that what's going to happen is that this delivery truck is going to come barreling in, and it's going to keep moving in the rightwards direction. So you have something with greater momentum, that's the delivery truck, and something with lesser momentum, that's going to be the pickup truck. And the delivery truck is actually going to sort of roll over the pickup truck, as if you will. Let's also assume that there are no crumple zones, and that these cars are going to behave, well, like model cars. They're behaving as perfectly rigid bodies. So in a collision, you can see where the thing with greater momentum will actually continue moving in the direction it was initially going. And I'm sure there are some simulations of this online. I'll try to find one and post it to this video, or linked in this video, where you can crash, semi trucks into scooters and that kind of thing, and see what happens. All right, so let's start analyzing the problem. The initial velocity of the delivery truck is 0.5 meters per second in this direction. The velocity of the pickup truck is negative 0.75 meters per second in this other direction. The reason we've defined this velocity as positive and this velocity as negative is that we have defined our x-axes as positive x going to the right. Okay? So we're asked to find the velocity of the miniature truck, or rather the F-150 truck. We apply our conservation of linear momentum formula. So we're going to call M1, sorry, this should be M1, and M2, and M1, and M2. We're going to call M1 this delivery truck, and V1I the velocity of the delivery truck, and we're going to call M2 the pickup truck. All right? We simply plug and chug. So we have the mass of the delivery truck in kilograms times its velocity in meters per second, plus the mass of the F-150 truck in kilograms times the velocity of the F-150 truck in meters per second. And then we say on the final side, it's 0.02 kilograms, that's again the mass of this delivery truck, times 0.1 meters per second plus 0.1 meters per second, because we're told that the delivery truck continues in its original direction at 10 meters per second. So that's where we get this 0.1 from, plus 0.05 kilograms, again, the mass of the F-150, times the final velocity of the F-150. And what we're being asked to solve is this, VF2. Well, that's pretty simple. That's just algebra. We go ahead and solve, and we find that VF2 is positive 0.85 meters per second. And because this is positive, that truck is moving in the rightward direction, or the F-150 truck is moving in the rightward direction. So basically, you get this kind of scenario. So I'm going to hold my fists off of the screen, and I'm going to have them collide. So they're coming in from the left and right side, bang, and then you get motion of both trucks in the rightward direction. All right. So just for fun, just to sort of rubberneck, if you will, in this auto accident, what's the change in kinetic energy and what kind of collision is this? So the delivery truck, we're told, has a mass of 0.02 kilograms. its initial velocity is 0.5 meters per second, and its final velocity is 0.1 meters per second. So if we find the initial kinetic energy just by plugging in 1/2 mv squared, we find it to be this very small quantity, I mean, these are rather small trucks, of 0.0025 joules. If we do that for the final case, we just run these numbers, we find it's 0.0001 joules, right? If we do the same for the pickup truck, we know the initial mass to be 0.005 kilograms, the initial velocity to be negative 0.75 meters per second, the final velocity to be 0.85 meters per second, and therefore the initial kinetic energy to be 0.0014 joules, and the final kinetic energy to be 0.0018 joules. What's interesting to note here is that the kinetic energy of the pickup truck has actually increased, whereas the kinetic energy in the delivery truck has decreased. However, if we sum these together, the total initial kinetic energy, so in other words, this quantity here plus this quantity here, leaves us with 0.0039 joules, but the final kinetic energy, which is, I'm going to switch colors here, this quantity here plus this quantity here is equal to 0.0019 joules. So there has been a loss of kinetic energy to the outside system or to the outside world as a result of this collision. However, as we saw in the previous problem, and indeed as we based our entire solving strategy around this, the linear momentum is conserved. So again, linear momentum and energy are not the same things, and you can conserve linear momentum while losing kinetic energy, as we just saw in this example. All right, so let's take a look at a perfectly inelastic collision. So this is something where the two objects are going to collide and they're going to stick together. Once again, linear momentum is going to be conserved. So P initial is going to equal P final. And we write in our formula as we've previously done. However, how are we going to handle the fact that M1 and M2 are going to be stuck together in a new particle, in a new combined particle? Well, it's a very simple adjustment. We just say that M1v1 plus M2v2 equals M1 plus M2 times velocity final. And this velocity final is the final velocity of that combined, stuck together particle. So again, very simple. Let's take a look at how to use that in an example problem. So we have two blocks with masses of 1.5 kilograms and 2.5 kilograms approaching each other with the following initial velocities of plus 2.0 meters per second and negative 3.0 meters per second, as shown in the diagram. The two blocks collide in a totally inelastic collision, which, as we've said, means that they stick together after they collide. We define the positive x-axis in this case by this arrow here. So positive x is moving towards the right. And again, it's very important to define your axes whenever you're looking at a problem so that you can determine what is plus and what is minus and what quantities you need to add and subtract together to get some kind of logical answer. All right? It's a quick public service announcement from this physics lecturer. Okay, so we apply our formula for a perfectly inelastic collision where M1v1 plus M2v2 equals M1 plus M2 times the final. Once again, we plug and chug. So the mass of mass 1 is 1.5 kilograms. The velocity of mass 1 is 2.0 meters per second, and that's positive. It's going to the right. In the second one, the second mass, the mass is 2.5 kilograms. The velocity is negative 3.0 meters per second, and it's negative because it's directed to the left, and we've defined positive x that way. So positive x is to the right, negative x is to the left. We then have the sum of the masses, so 1.5 kilograms plus 2.5 kilograms times velocity final, and we're trying to solve for this quantity, velocity final. So we just evaluate and rearrange. So I've summed these two parts here, and I've divided by this sum here, and we find that, whoops, velocity final is equal to negative 1.1 meters per second. So a pretty straightforward thing. Again, you just have to get used to the fact that there is a combined final velocity and a combined final mass in these sorts of perfectly inelastic collisions. So let's take a look at elastic collisions. And we're going to kind of skip this derivation, but just so you know where it comes from, where the equation I'm about to show come from, here are sort of the underpinnings, if you will, of those equations. So in an elastic collision, the conservation of linear momentum applies. So momentum initial equals momentum final. And then we have, again, m1 v1 plus m2 v2 equals m1 v1 plus m2 v2 in the initial and final conditions. Also, because this collision is elastic, the conservation of kinetic energy applies. So the initial kinetic energy is equal to the final kinetic energy. We then say, okay, what are the formulas for kinetic energy? And this is what we come up with. And this is what we show once again down here. After we do a little bit of algebra, and I'm not going to show it here, but trust me for just a moment, what we eventually find is that V1 final is equal to M1 minus M2 over M1 plus M2 times velocity 1 initial plus 2m2 over m1 plus m2 times v2 initial. And v2 final, the final velocity of the second object in the collision, is equal to 2 times m1 over m1 plus m2 times v1 initial plus m2 minus m1 over m1 plus m2 times velocity of the second object initial. All right, so again, kind of handy formulas. I'm pretty sure this is on the equation sheet. If it isn't, I will make sure it gets onto the equation sheet. All right, so in the figure here, the masses of the blocks and the velocities before the collision are given. If the collision is modeled after an elastic collision, then what are the final velocities of the objects? So once again, what we're going to want to do is define what positive x is. We're going to define this as mass 1. We're going to define this other mass as mass 2. We pull down our equations from the previous slide, and we substitute accordingly. So velocity of this first mass is equal to 4 kilograms, its own mass, minus the mass of the second object, or 6 kilograms, over 4 kilograms plus 6 kilograms, times the initial velocity of the first mass, which is 1.8 meters per second, plus 2 times the mass of the second object, so 2 times 6 kilograms, over m1 plus m2, so that's 4 kilograms plus 6 kilograms, times the initial velocity of the second mass, which is negative 0.2 meters per second, because it's 0.2 meters per second directed to the left, and we have defined our positive x-axis as being to the right. So this is negative 0.2 meters per second. You go ahead and evaluate this, and you should find that the final velocity of the first mass is negative 0.60 meters per second. So what that means, if we're going to draw that out, is that this first mass is now moving in this direction at 0.6 meters per second. Okay? Then if we do the same for the second mass, I'm just going to sort of put this up here. And again, you can find where everything corresponds to everything else, right? But the final answer is 1.4 meters per second. And this is positive, meaning that the motion is to the right of the 6 kilogram mass, and this is 1.4 meters per second going to the right. Again, notice that the velocities of each of these objects are not equal in magnitude to what they were before the collision. So this block is moving at 1.8 meters per second to the right, and now it's only moving at 0.6 meters per second to the left. Similarly, in the 6 kilogram case, this is coming in very slowly at 0.2 meters per second to the left, and it springs off of the collision at 1.4 meters per second to the right. So while we would expect the directions to be opposite in direction, we should also note that the velocities, or the magnitudes of the velocities, have also changed. The total kinetic energy of this system is conserved. However, the kinetic energy of the individual particles, the individual participants in the collision, can and does change, as we've seen in this example. Okay, so let's try something a little more complicated. Let's say that Bert strikes a cue ball, which is 0.17 kilograms, at a velocity of 3 meters per second in order to get the 8 ball, to shoot the 8 ball into some pocket here. The cue ball's mass is 0.16 kilograms. The path of the 8 ball and the cue ball after the collision is given by these angles. So the 8 ball, after being struck, goes off in this direction at a 45-degree angle, whereas the cue ball goes off in this direction at a 40-degree angle from the horizontal. And again, let's say for the sake of argument that this horizontal goes right through sort of the center of that collision, if you will. All right, so how are we going to find the velocity of both the cue ball and the 8 ball after the collision? Well, to find the velocity, you have to find the momentum after the collision. So if you can find the momentum of this 8 ball as it's going in this direction, you know the 8 ball's mass, and therefore finding the 8 ball's velocity should be very easy. Similarly, you know the cue ball's mass. If you can find the cue ball's momentum, you can find the cue ball's velocity. Even better, because velocity is a vector quantity and momentum is directed in the same direction as the velocity, if you can find the momentum vector, you can then find the velocity vector very easily. But how are we going to do that? Well, we have to remember that linear momentum is conserved. What exactly does that mean in this particular case? Because now we're dealing with a collision in 2 dimensions. Well, and actually I'm not sure if I defined my axes. Let's go ahead and define them this way, that this is plus x and this is plus y. I know I did that on the later slides ad nauseum, but what we mean by linear momentum being conserved is that the momentum of the system in the x direction and the momentum of the system in the y direction is going to be the same before and after the collision. What this means in equation form is that the momentum of the cue ball initially before the collision and the momentum of the 8 ball initially before the collision in the x direction is going to be equal to the momentum of the cue ball in the x direction after the collision plus the momentum of the 8 ball after the collision in the x direction. Same story with the y direction, or the y, same direction and same story in the y dimension. that the momentum of the cue ball in the y direction plus the momentum of the 8 ball in the y direction initially, before the collision, is going to be the same as the sum of the momentum in the y direction of both the cue ball and the 8 ball added together. In this case, what you should notice is that because the cue ball, after the collision, is going in a negative y direction, its momentum will also have a negative y component. Whereas for the 8 ball, the momentum and the velocity is going to have a y component, meaning that the momentum is going to have a positive y component. So what we expect is for the y component of the momentum of the ball, of the cue ball, after the collision, to be equal in magnitude and opposite in sign to the momentum of the 8 ball in the positive y direction. Okay, I'm going to show this with equations and everything in just a little bit, but conceptually, that's sort of where we're going. All right? So we can simplify this actually rather nicely, as there is no momentum in the y direction initially. So this ball here, which is being struck on the horizontal. There is no y component to the velocity vector, and therefore no y component of the momentum vector. So we can say that the initial momentum in y of the cue plus the initial momentum in y of the 8 ball is equal to the final momentum in y of the cue ball plus the final momentum in y of the 8 ball, and that equals 0. So in other words, these two things are going to be equal in magnitude, but opposite in sign. We also know that all of the momentum in the x direction initially is in the cue ball. So this collision has a stationary 8 ball and a cue ball that comes screaming in to strike it. Because the 8 ball is not moving before the collision, it has no momentum. So any linear momentum in the x direction before the collision is the momentum that comes out of the cue ball, the only thing that's actually moving. So we can say that momentum q initial, that's the only thing that we care about, is equal to m times vx initial, again, of the cue ball. So 0.17 kilograms times 3 meters per second equals 0.51 newtons times seconds. So when we take a look at the final in x here, we know that this is going to end up equal to 0.51. All right? Okay, and we know that this quantity here, which I'm striking out, is 0. Okay. So just once again, pxq initial plus px8 initial is equal to pxq final equals px8 final, and that's going to equal this quantity. Once again, we know that this is 0. So that's where we got the 0.51 newtons times seconds from. We just looked at the momentum of PQ initial because we see that, because that's what we know. All right. Okay. So now I've kind of nicely defined my axes. Sorry, I didn't do that before. Let's define these sort of triangles. Let's split the momentum vectors into their x and y components after the collision. So here outlined in red are the momentum vectors, or the components rather, of the momentum vector of the cue ball after the collision. We have that 40-degree angle. These are the components of the momentum vector of the 8 ball after the collision. So first, let's take a look at the y component half, the y component part of the picture. We know that the momentum of the 8 ball in the y direction, final, plus the momentum of the cue ball, final, again, after the collision, is going to have to equal 0. We can then substitute what that's going to be in terms of the overall momentum vector of the 8 and of the Q. So I've just drawn those in there. So P8 final times sine of 45 degrees is the y component. PC final times sine of 40 degrees is the y component down here. And we know that that all equals 0. Now let's take a look at the x half, or the x components. We know that the momentum of these two components added together has to equal 0.51 newtons per second. That has to be equal to the initial momentum that was provided by the cue ball in the x direction. So in this case, if we have the magnitude of the momentum vector, P8 times cosine of 45, that will give us the x component, and then the q momentum vector times cosine of 40, that will give us the x component. We make those substitutions appropriately, and there you go. So now we have a nice system of equations. We have P8f times sine 45 minus PQF times sine of 40 degrees equals 0, and P8 final cosine 45 plus PQ final times cosine of 40 equals 0.51 newtons times seconds. We can solve. To solve the system, we solve for this quantity here, so PCF, and that's just a very simple matter of bringing this guy over to the right side of the equation and dividing by sine 40. So from this equation, here is where we're deriving this. All right, and I just want to give everyone a moment to see that. Okay? Okay. Next thing we can do is, now that we know what this is, in terms of the momentum on the 8-ball final, we take this whole business here and we plug it in right here. Right? So when we go ahead and plug it in, this is the resulting equation. And now we have one variable, one equation, and we can find everything else out. We then go ahead and do some rearrangement, and we find that 0.7071 P8F plus 0.8427 P8F is equal to 0.51 newtons per second. And so we find that the magnitude of this momentum vector for the 8-ball in the final direction is 0.33 newtons times seconds. Okay, so that's pretty cool. And I kind of dropped the vector notation here because you are dealing with magnitudes down here. All right, so now to find PCF, what we do is we simply take this value here, and we can plug it in up here, or alternately we can plug it in down here. It's a little bit less drawing. Evaluate, and we find that the magnitude of the cue ball after the collision is 0.36 newtons times seconds. Right? So now let's finish up the problem. We know what the magnitudes of each of the vectors are. We have our vector definitions. As a sanity check, I'd recommend writing the momentum vectors just to make sure that linear momentum is conserved. So here's where we're looking at the 8-ball, the behavior of the 8-ball. And we know that P8 final is equal to the magnitude of that final vector times cosine of 45 degrees I cap, that's the x component, plus 0.33, again the magnitude, newtons times seconds, times sine of 45 j cap for your y component. And you go ahead and find that it's 0.23 newtons times seconds I cap plus 0.23 newtons times seconds j cap. All right. Then we do the same thing for the cue ball. We find that the final vector that we get should be 0.36, again, the magnitude of the cue ball's momentum, times cosine of 40. So again, 40 degrees, you're looking for the x component, cosine of 40, I cap, minus 0.36 newtons times seconds, sine of 40 degrees, j cap. Why are we calling this minus? Well, if we come back to our axis definition, this is plus y is this way, that's plus y, meaning that the y component of the momentum of the cue ball is negative. So you need to subtract here. That's why this sign is negative. All right. So once again, you go ahead and evaluate, and you find that the final vector for momentum of the cue ball is 0.28 newtons times seconds I cap minus 0.23 newtons times seconds j cap. Well, as a final check, and the reason that I recommended writing the momentum vectors first before you write the velocity vectors is, if you take a look at this over here, and you take a look at this over here, you'll find that the sum of these is 0, which is, as we said when we started the problem, what's supposed to be happening here. That's exactly what we expect. And if you take the sum of this and the sum of that, you're going to find that that sums to 0.51, which is, again, what we expected. So it sums in x is 0.51 and sums as y in y as y equals 0. And we know that linear momentum is now conserved by this answer, and we take a big sigh of relief. In fact, when I was working this problem earlier, I had made a mistake with the decimal point, and I was finding that the vectors I was getting did not add up to what I was expecting them to be, or what they should be in this case, which then caused me to look back over my work and do this correctly, and then demonstrate it correctly in this video. So it's very important to do this kind of sanity check. Are you getting the answer that you should be getting just by sort of, taking another look at it, right? So to get at the velocity vectors, remember that momentum is equal to mass times velocity. Therefore, the velocity vector is equal to momentum over mass. So we know that the momentum of the cue ball is given by the velocity of the cue ball is given by the momentum of the cue ball over the mass of the cue ball. We go ahead and we find that the velocity, final velocity of the cue ball is 1.6 meters per second I cap minus 1.4 meters per second j cap. Similarly, if we do this in the 8-ball, we find that the final velocity is 1.4 meters per second I cap plus 1.4 meters per second j cap. And these would be the final answers to your problem. Well, that was fun. Let's take a look at just one more problem, last example. But if you were able to follow the last one, and perhaps if you want to go over it yourself as a sort of exercise, I think you're getting a pretty good grasp of what momentum is and what it does and how we can solve problems with it. So go ahead and pat yourself on the back. I know I did. And then let's take a look at this next doozy. So we know a 12-gram rifle bullet is fired with a speed of velocity bullet in meters per second into a woodblock pendulum with mass of 6.00 kilograms, suspended from 2 cords 70.0 centimeters long. The bullet embeds in the block, and the block swings upward after impact. If the bullet block system reached a maximum height of 29 centimeters, then what was the muzzle speed of the bullet? Now, I actually kind of like this problem because you're going to find that a fair amount of information that was provided to you is actually irrelevant and is not necessary to solve this particular problem. Let me show you what I mean. So, what kind of collision is this? It's perfectly elastic, or totally inelastic, or completely inelastic, or just incredibly inelastic. You know, this is the most inelastic collision ever. Believe me, it's just completely inelastic. All right. So what we use is this equation: m1v1 plus m2v2 equals m1 plus m2 times velocity final. The velocity final in this case is going to be the velocity taken by the block-bullet combination. And the mass is the mass of the bullet plus the mass of the block. So we also know that this second mass, so this is what we're calling m2 here, is this block mass. M2 V2 initial is equal to 0 because this block is just hanging out. This block is not moving at the beginning of the problem. So we have the mass of the bullet, or 0.012 kilograms, times the velocity of the bullet, plus 0, equals the mass of the bullet plus the mass of the block times the final velocity. Now, we have a problem because we're asked to find V1. We say, well, that's fine, but we don't know VF. We don't know this quantity yet. So how are we going to solve this problem? I'll give you some time to work it out. So how are we going to work this problem? Well, as you may have seen, because I didn't put in the animation correctly, oops, the energy initial plus the work done by non-conservative forces is equal to energy final. This is a highlight from a previous chapter. Well, what's that have to do with anything? Well, think about what happens to the block after the collision. All of the initial energy is kinetic. So let's say that we take as our initial condition the bullet striking the block and the block swinging upwards. So let's say that we have some sort of intermediate stage here, and we've got our block, and our block is swinging upwards, and let's call that some kind of initial condition in our work energy problem. All of the initial energy that this block has is kinetic. And all of the final energy is potential. We're told that this block is lifted a distance of 29 centimeters. So if we define some axis here for our y coordinate, ooh, that sounds familiar, and we say that the displacement from this y coordinate is 29 centimeters, well, that sounds promising. We might be able to do something there. And all of the final energy here is potential. Let's assume, again, no friction on the part of this block system. So all of the work that is being done as this block is being lifted upwards and then eventually being returned to rest, as it's both going up and down, is done by a conservative force. Okay, so you have some energy initial, and then you have no work being done by a non-conservative force. Again, you might be saying, well, I mean, there is this force of the bullet that's striking the block, but for the purposes of this problem, let's say that our initial condition is that the block already has that kinetic energy. We're not going to worry, again, in this part of the problem, we're not going to worry about how it got that energy. We're just going to say it has enough kinetic energy to lift the block 29 centimeters. So all the work is done by a conservative force, meaning that the work done by non-conservative forces is equal to 0, meaning that the energy initial is equal to the energy final. And all of that final energy is in potential energy. all of the initial energy is in the kinetic energy of the block after it's been struck with the bullet and is moving. So you can say that Ki initial equals U final. So 1/2 m1 plus m2, again, we're concerned with the mass of the block and bullet system, times Vf squared, and that's Vf. The reason I called it Vf is it's this guy. So these guys are the same, is equal to mgy. And that's mgy when this block is lifted to its final position. Okay? So we know that Ki equals Uf. So 1/2 m1 plus m2 Vf squared equals m1 plus m2 Gy squared. Again, these are the same masses, right? So we go ahead and substitute for G, the acceleration due to gravity. We know that our y-coordinate, if we defined our y-axis as going through the center of this block's position, we know our y-coordinate is 0.29 meters. Okay. Then we can go ahead and evaluate. So these masses will cancel. We bring the 1/2 to the other side of the equation. So the 1/2 ends up going over here. You multiply both sides by 2. Then you take the square root, this is v squared. You find that Vf squared is equal to 2.38 meters per second. All right, now we're in business. Now we're in business. You go back to where you were, where you're taking a look at the conservation of momentum when this bullet strikes the block and drives it upward. We again know that it's the mass of the bullet times the velocity of the bullet plus 0. There's no momentum in this block. We now know what V final is because we worked it out using the potential energy, or rather the work energy theorem. We can go ahead and plug in, and we find, okay, I didn't really need to do that, but this is the substitution that you're doing. You evaluate, and you find that the initial velocity of the bullet is 1,194 meters per second. So there's a very kind of cool interrelation between the work energy theorem and the things that we're learning in this chapter about momentum. So physics is cumulative, and it's a wonderful thing. So that concludes the lecture notes for part 2 of chapter 8. Next time, I'm going to be talking about center of mass, or if you're British, centre of mass. So I hope you enjoyed this lecture, and I will see you next time.